Okay, for all the students of calculus 3 who find it hard to visualize the Riemann sums, okay, let's recall calculus 1 and the Riemann sums in calculus 1 when we approximate an area under a curve. In calculus 3, however, we're gonna approximate using Riemann sums an area, not an area, but a volume under a surface. So instead of calculus 1 approximating area under a curve, in calculus 3 we're gonna approximate a volume under a surface. Okay, now recall n is a number of rectangles with which we're gonna approximate the area. So our function is, I don't know, I just invented it. Okay, minus 2/3 x to the power of 3 plus 8x squared plus 2x plus 17. Okay, we have our parameters a to b, which means it's the range, because this function is only in one dimension, one variable x. The range gonna be from a to b, from 2 to 10. And from 2 to 10, we're gonna create 8 delta x, okay? 8 rectangles, okay? So let's define the function. Let's load ggplot. We don't need plotly, okay? We take these parameters, blah blah blah, 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 and let's see what's going on, okay? And that is a Riemann approximation, Riemann sums, okay? Now let's take n. You see 1, 2, 3, 4, 5, 6, 7, 8. Let's make it 16. You see, we approximate, it's not accurate. You see, we are wrong. Sometimes we miss. Okay, we don't take into account this area under the curve. But sometimes we overshoot. Okay, so suppose we're gonna make this delta x as a width of each segment here, of each rectangle. We're gonna make it smaller. How can we make it smaller? We make more rectangles. If instead from A to B, from 2 to 10, instead of 8 rectangles, we're gonna have 16. So each rectangle is gonna be half the width. Yeah? Half the width. So we're gonna approximate it much better. Okay? So let's do it again. Just with 16. That's the only difference. Yeah? Okay? Much better. You see? Much better approximation. Okay, let's make it 32. Now, let's see what is going on. Much better. Much better. Let's take it, I don't know, 64, 128, 256. Let's take it to 256. Okay, 256. Gonna be much better. Much better, okay? This is very good approximation. Now suppose we're gonna let n, the number of rectangles, approach infinity. Approach infinity. Okay. what's gonna happen to the width of each rectangle? It's gonna collapse, it's gonna squeeze and approach 0. So delta x will become dx. And that is an integral. Integral is just a sum of infinite, okay? It's sum of infinity. Instead of we are summing the area of 8 rectangles, of 16 rectangles, of 32 rectangles, of 256 rectangles, we're gonna sum the area of infinite number of rectangles from x equal 2 to x equal 10. And recall, for each rectangle, okay, so let's move here, for even here, for each rectangle, we randomly pick a point, and then we plug that point, we plug it in the function to evaluate the height of the value of the function in that random point. So we have this. Let's look here. Okay, we take, let's say, the third rectangle. Okay, the delta x is wide. Okay, so we have a lot of x values around here. Yeah, if this is 4, this is 5. So we have from 4 to 5, infinite number of x's, but we choose one randomly. Yeah, here you see it here, set seed. Okay, it's random. Okay, we pick a point randomly. Okay, we plug it in the function to evaluate the function in that point, in that random point, in the third segment, the third rectangle. Yeah, we evaluate the function at that point, and that gives us the height of the rectangle. Okay, that's what gives us the height of the rectangle. Now suppose we take n to infinity. So we have infinite number of rectangles in this region from 2 to 10. So the width of each rectangle gonna collapse to 0. So delta x becomes dx, and this is like approaching 0. So what does it mean? It means each point we evaluate, we have infinite points now, randomly picked points to evaluate. So we evaluate each point of the function. Okay, this is what happened in 256. It becomes so narrow, okay, that even if we let's zoom. Okay, even if we okay, even if we go here, you see we have a little bit of width. Yeah, we have little bit of width. So we have like x's, different x's to pick randomly. So we're gonna miss. It will not be accurate. Yeah, it's approximation. But suppose it becomes 0. It's collapsing, squeezing to 0. So each point in this function you're gonna evaluate. Okay, and that is an integral. Why Leibniz denote the integral symbol with s, because it's a sum, but it's a sum of infinite terms. Okay, now let's move on. Let's advance to calculus 3. Okay, so let's delete everything around here. Let's also delete the environment. We don't want it now. Okay, and move forward to calculus 3. The only difference here, we're gonna have another variable. Let's call it y. So now we have a function of x and y. So we're extending the dimension. It's now 3D. Okay, so instead of rectangles, instead of summing up, adding up the area of 8 rectangles, 32 rectangles, 256 rectangles, infinite rectangles, what now we have another dimension, so we extend it to 3D. So we gonna sum up the volume of rectangular prisms. Okay, so imagine we have a rectangular prism. Okay, so we're gonna evaluate its volume. Okay, because again we're gonna partition our x-axis, the region. Like here we have the range from 2 to 10. Okay, and we decide from 2 to 10 to have n equal 8 or n equal 32 or 256, blah, blah, blah. And that gives us the delta x, the width of each segment in x. Yeah. And we said that when we approach n, when we let n approach infinity, delta x approaches 0 and become dx. Now we're gonna do the same for y. We do it the same way we did it to x, but we do it as well to y. So we're gonna have, instead of delta x, we're gonna have little rectangles with area of delta x, delta y. That is the area. What is the area of a rectangle? Width times length. Okay, length will be delta y, and the width gonna be delta x. Now what gonna be the height of the function? We have a function of x and y. So the height of the function, if we pick in each of our, let's say we partition our x-axis to m parts, okay? And the y-axis to n parts. Let's say m is 8 and n is 10. So we cut the y-axis to 8, to 10, and the x-axis is in the region, okay, to 8. So we're gonna have how many rectangles defined by delta x, delta y with 80, yeah? 8 times 10, 80, okay? Now for each of these 80 little rectangles, sub-rectangles, let's call it like that, okay? We're gonna randomly pick a point. So that point, it's gonna be xy point. It's gonna have a value in x and a value in y. Okay? For example, x equal 1.5 and y equal 2 point, let's say, and 1, and I don't know, and y equal 0.05. Okay? We evaluate the height of the function, the value of the function in that xy pair, and that gives us the height of this sub-rectangle. Okay? And so we take the area of that sub-rectangle, which is delta x, delta y, times the value of the function of a randomly picked point of that sub-rectangle. And if we take an area of a rectangle times the height, we're gonna get a prism, a volume. Okay? Volume. So we got that's what we're gonna do. Okay? So here we let, okay, I need to be consistent and do it good. Here, what happened? we partitioned it to 16, okay? Only 16. But both of y and x. So m equals n equals 16. So if we have 16, if we cut the y to 16 and x to 16, so what we're gonna have? 16 times 16, 256, isn't it? Yeah, I'm sure. It must be. 16 times 16 is 160. Yeah, 96. Yeah, 256. So we have 256 rectangles, subrectangles in the y-x plane. Each of them, we're going to randomly pick a point to evaluate f of x and y. And that will determine the height of the function at that particular point of that subrectangle. Yeah? Okay, that's what we're going to do. So that is our function. 16 minus x squared minus 2 y squared. Okay, let's do like that. It's gonna be nice. Okay, so we have 16 minus x squared minus 2 y squared. Okay, so yeah, let's upload this library. Let's define the function. Now the range is gonna be right now in both x and y axes from 0 to 2. Okay, and now I wrote a big function I wrote a very big function. All of that stuff. Okay, let's see what happens. This is our function, the surface here, the green color here, and we have these rectangular prisms that we approximate the volume under the surface described by our function. We approximate this volume with our rectangular prisms. Okay, so slowly but surely they are building up. We are summing them. If you see how we are summing them. It's nice because we have a double sum in the notations. We have double sum. Okay, so if you have an acute brain, what you're gonna find out that for each x value, okay, we approximate all the we add up all the we sum up all the y's. Look, that is the axis, okay, that is the axis, and that is the y axis. So we stop here in that particular x, and we add up all the y's. Only then, when we reach here, we're gonna move to the next x and sum up all the y's. Okay, we could have done it in the opposite way. We could have done it, hey, stop at the first y and sum up all the x's, then move to the next y. Okay, it's the double sum. You have a creature for like xij and yij, and you're gonna sum it for I and for j. Okay, so if we determine, for example, that x is I and y is j. What is going on here is that we are summing up, if x is I and y is j, we are summing up all the j's for each I. Okay, so the first sum in the notation will be sum from I equal to 1 to m, and the second sum gonna be from j equal to 1 to n. Okay, and therefore for each I we're gonna sum up, add up all the j's. Okay, because we take the inner sum for each I in the outer sum. That's how it works. It's very important concept when we're gonna take it to infinity, because here we're gonna say, hey, I don't want 256 rectangular prisms. No, I don't want, I want infinite number of prisms. How can we do it? If I take in the number of, you see here, y, we took y from 0 to 2 and we broke it to 16 segments, 16 rectangles. Yeah, so each got a width, okay, 2 by 16, 1 to the 8th, okay, so each got a width delta y. If now let's say we let n becomes infinity, approach go to infinity, so delta y will be dy, and we're gonna have an infinite number of rectangles along the y-axis. The same we're gonna do for x. We're gonna let m goes to infinity. Yeah, okay, if we let m goes to infinity, we're gonna have an infinite number of rectangles along the x-axis. So if we have infinite number of rectangles along the x-axis and along the y-axis, so in 2D, if we look at the xy plane, only the xy plane, we're gonna have infinite number of rectangles with the area of each rectangle dx dy, and then if we squeezed each delta x and each delta y to dx dy, they approach 0. So we're gonna have all the points, okay, all the points of the function here. So when we gonna evaluate, you see we have these points, red points like indicate the randomly chosen point for each rectangle, okay? But you have a lot of different points or in each rectangle, a lot of different points. Yeah, we choose randomly one, so it's only approximation. But if we squeeze delta x to approach 0 and delta y to approach 0, so this rectangle with area of delta y, this is delta y, this is delta x, this approach 0 and this approach 0, it becomes, the area approaches 0. So if I now pick randomly I pick a point, I have no space to choose from. Each rectangle essentially will represent a point. Okay, so this rectangle will be very close to this rectangle. Yeah, the point here and the point here will be very near. Must be. It's gonna be smooth. Okay, so for the along the x-axis, along the y-axis, so along all these 2D space defined by x and y. Then, if we approximate each of these points, okay, it's gonna match up exactly to the function, and that is double integral that you find it hard in, I don't know why, in calculus 3. Okay, when you do double integral and you have the double notation, and it's very important to know what is the first notation and what is the second, because it's correspond to dx dy. So you have the inner integral and the outer integral. It's very important. Okay, so yeah, but everything comes from here, from the Riemann double sum. Okay. Yeah, and take care and have a nice day. Bye bye.